If the quantum computers are so useful, why hasn't nature, or has nature, after billions of years of evolution, basically stumbled on those principles?
Hey guys, I'm Eric Olson, and welcome to the Science-Centric Podcast. A little over a week ago, Google announced they had achieved something called quantum supremacy. It sounds a little nefarious, right? Like some kind of evil plot to take over the world. While we can all relax at least a little bit for now, it turns out that the supremacy is just a powerful new way of computing that makes use of quantum principles. Google claims its quantum processor can tackle a really difficult computational problem in about 2.5 minutes, a task that would take the fastest classical computer about 10,000 years. Researchers at IBM have contested that estimate, perhaps because they own the fastest classical supercomputer, and dialed it back to only 2.5 days. Whatever the true number, we know Google's processor is really fast, faster than any other computer preceding it, and powered by quantum technology. What do I mean by quantum? Well, that's a very large can of worms. Fortunately, our guest in this episode, science writer George Musser, is going to help us unpack what it all means. George has been writing about astronomy and physics for over 25 years. He's a contributing editor at Scientific American magazine and author of the book Spooky Action at a Distance, all about the strange phenomena called quantum entanglement. So stay tuned and prepare to feel your consciousness expand as we jump into the weirdness of the quantum realm. But before we dive in, head over to sciencecentric.com/support to help keep this video channel going. We accept donations via Patreon and also get a kickback on any purchases made through our website at no added cost to you. Other ways you can show your support are liking and sharing this episode, and of course, subscribing to the channel. Okay, enough of that. Let's get on to the good stuff. George Musser, I'm so glad to have you here finally on the podcast. I've been trying to get you on. For those in the audience that don't know, George and I have known each other quite a while now, I think. We worked together for a period of time at Scientific American magazine. He starred in many of my videos that I produced when I was there, and you're just always so interesting to talk to, because I think we come from a little bit. The worlds we come from are pretty different. You are deep into the physics and math and astrophysics, astronomy stuff, and I'm come from a biology background. Primarily genetics, a little bit of physics, muddled my way through enough to get my degree done. But anyways, welcome.
Thank you so much, and it's always a pleasure, Eric. We've had some great conversations over the years. We really have some adventures together.
Yeah, for sure. We could talk about that maybe in a little bit.
Yeah.
So I've been wanting to get you on the podcast, and I think this time period is really good because there was some news out from Google last week and a paper published, I believe, about the quantum supremacy, which sounds like a nefarious plot to overthrow the world. Maybe a Tom
Clancy's next novel, right?
Yeah, James Bond movie. So. And you really are like an expert on, quantum. You've written an entire book on quantum entanglement called Spooky Action at a Distance. So I think the timing is great. But, maybe for people that aren't super knowledgeable about quantum physics and stuff like that, what does quantum actually mean? The term gets thrown around a lot in marketing speak and, new age gurus and things like that. So when we're talking about quantum supremacy, quantum mechanics, quantum entanglement, what does that mean?
It's a good question, and it's one of these words that acquires its meaning by being used, in a sense. The original kind of etymology of the term is the idea of discreteness. So the idea that nature is particulate, it's not a continuous fluid. It's actually can be broken down into little particles. And moreover, that the particles have properties like energy or momentum that are discrete in their values. They can't take on any values. It's more like a ladder of values. But that original etymology, we're so beyond that now in the understanding of the world. For a long time, I would then default to saying, well, quantum physics is the physics of the micro world. It's the physics of the atoms, the electrons, photons, particles. But I can't do that either, because one realization, really from early on, but more reinforced of late, is that quantum physics applies to everything in the world, including us. And that's kind of one of the mysterious or unresolved puzzles of quantum theory, is how it can apply to us when we seem so unquantum in our nature. So some aspects of the quantum realm that came from the particle, the atomic level, are things like wave behavior, that particles had this kind of odd particles and us. So when I use the word particle from now on, there should be an us in the
well, right? we're essentially a collection of particles, right? I mean,
we are, but moreover, we can be taken in our entirety. Our entire body could, in principle, be considered a particle for the purposes of the analysis. So it's not just that we consist of particles; it's that also at the level of the human, or of the dust grain or the moon or any objects, you can treat them for some purposes as a single entity.
Okay.
So I can talk about myself. And this is like when you go back to the Schrödinger cat. Maybe we should start with the Schrödinger cat, because I think that's a very illuminating experiment. And the whole purpose of which, so Schrödinger developed that idea in 1935. And the idea was precisely to connect it wasn't to make cats into this kind of weird icon of science. It was to connect what's happening at the atomic level with what's happening at the macro level. And actually that there would be a connection, that if a particle can be put into this weird state of ambiguity, this is one of the features of quantum physics, weird and state that seems to us ambiguous, between saying it's decayed or not decayed, or it's here or there, or it's up and down. It depends. There's different things you can say it's X and Y, and the X's and the Y's can vary.
So for people that are listening, the Schrödinger's cat, there were no actual cats involved. It's a thought experiment where this cat is put into a box, right? And there's this sort of mechanism on the outside of the box that is influenced by particles, and if the particles hit this detector in a certain way, it will release a gas and kill the cat. And if it doesn't hit it in a certain way, then it doesn't, and the cat stays alive, right? So
that the point being that the atom in this case is in some kind of ambiguous condition. And we can parse what that means, because that's actually interesting in its own right. But just take this ambiguity. It's ambivalent. It could either have decayed or not decayed at any instant. So it's 12 o'clock, it could have decayed or not decayed. It's 1 o'clock, could have decayed or not decayed. So we don't know what state at any given time. And then that ambivalence is transmitted to the cat. And in the original experiment, it was through this kind of poison gas, but it can be done in other ways as well that are not so morbid. But the point is that the cat then enters a state of ambivalence, in this case, between being alive and dead. And you wonder, well, first of all, how can a cat be alive and dead, or in an uncertain condition of being alive or dead? Second, that when you open the box, you look in, you see a cat alive or dead. So not only is it ambivalent, which is already bad enough, but its ambivalence is never directly observed. And this is a very peculiar feature of the quantum world, that it seems to work on two levels. There's this kind of base fundamental level where there's ambivalence and weird effects. And then there's the higher level in which we operate, where we don't see those. And the connection between them has never been clear. This is literally a century after Einstein started to develop the theory, and others came in, that we still don't know. And the same kind of ambivalence, this kind of two-level description is a problem with waves and particles. You sometimes hear, is it a wave or is it a particle? The wave is basically the lower level, and the particle is the higher level. We don't see these waves, these putative waves in nature. We only see particles, but they behave like there's waves.
Yeah.
So why? And this kind of goes under the rubric of what's called the measurement problem. And you could probably argue that it's the number one unresolved problem in physics, because everything else in physics, astrophysics, galaxies, universe, everything kind of hinges on this problem.
Yeah.
It's always, all of those things are in a way mysterious, and if we don't understand how these levels of quantum mechanics relate to one another.
So you're saying that, I mean, to bring it back to Schrödinger's cat, essentially that cat is in this state of kind of quantum flux, if you will, or flux between alive and dead. But that's not how we experience the world, right? I mean, so when you're saying that like we are quantum, it just doesn't make any rational sense to think it, because we don't experience the world that way. We experience it in this very like Newtonian, either or sort of state. It's not this weird quantum things popping in and out of existence, various states. So like what, I mean, I don't know. I guess I just don't get it, but.
Well, you shouldn't get it because it's not God. It's not something human beings have really got. Now, people can kind of analyze it. So there's been a lot of progress on kind of sharpening the question here.
Yeah.
But ultimately, and I think you grammatically had it there, you start with an and you end up with an or, and it's not clear how that conjugation or that conjunction changes there, and why we can indirectly see that our objects in the world have a wave-like character. And what that means in terms of particles is the particle can be here and there.
Yeah.
Now, let me actually footnote that because I want to come back to what that actually means. But for the time being, we can simply say the particle's here and there. But when we look at it, of course, it's either here or there.
Right.
And how does that occur? We can sort of get at it. There's ideas like what it was known as decoherence, partly answer the question. It answers the issue of categories, that the here, there, other places, those boxes, spatial in this case, boxes we put things in, can be understood through this process of decoherence. But the final decision, which box does the particle land in? Is it here, there, on the moon, wherever? Is not yet resolved.
Yeah.
And there's a lot of ideas that people have put out that are all very interesting. This is where you started getting into ideas of multiple universes, and there are ways to understand this multiplicity of possibilities. Now, one thing, I come back to that footnote that I had said earlier. It's partly a question of our categories. So to take the cat as an example, the cat is in human or even cat terms alive or dead. Those are very important categories, alive or dead, to us. However, they don't exist in the quantum world. So when the cat is put into this ambivalent state of alive or dead, it's not ambivalent in quantum terms. It's a perfectly well-defined state that just so happens to sound very weird. The cat is alive plus dead. And you can make it maybe kind of 40% alive and 60% dead, or you can go to 70-30. You can kind of those. And those are all meaningful states in quantum theory.
Yeah, right.
So when the cat is moved into one of them, it's not that it, and this is why when people say it's alive and dead, it's a little bit of a grammatical slippage, because it implies an uncertainty or an ambivalence that actually the quantum does not possess. It's just that the quantum state doesn't translate into a human category or line category that well. I'm probably throwing too much out.
Well, I think maybe you could say that it's very unintuitive or unintuitive to us to think in those terms.
Yeah, and that's good. You kind of want that because you want physics to tell you the world is weird, or rather, the world is different from our intuition. Because our intuition's evolved on that savannah, we're chasing antelope or whatever we were doing back then, and it's actually, we should just be grateful that we can understand the microphysics at all, given that our brains didn't. So it's going to seem strange to us.
And there's all kinds of things happening around us that our brains and bodies are not attuned to, right? I mean, there's all kinds of electromagnetic waves zipping around us at any given time, and we're just oblivious because our eyes and our sensory organs can't pick those up. So I mean, maybe this is just beyond the capacity of our, what we evolved to comprehend.
One thing I do want to argue, I have a forthcoming book that will explore some of the interconnections between physics and neuroscience, psychology, and AI.
Yeah.
And one thing I'm going to argue in that book is that our brains can understand this. That I'm going to have a kind of hopeful outcome here. I think there's a kind of universality to human reasoning that has gotten us this far, and there's no reason to think it'll stop working now, even for these big questions of what is consciousness, or what is the quantum world, or what's the beginning of time. But we have to find a way to do it.
Yeah.
And that's where we're stuck right now.
Right. One thing that I wanted to bring up with you is that, and I mentioned this at the beginning of our conversation, that there are some people in sort of the New Age movement that have capitalized on this idea that things don't really exist or aren't the way that they really are, and or we can think about them differently, and then that will sort of change our reality. And I think on a psychological level, that probably makes sense. Like, it's good, it's that old adage that if you believe you can or you believe you can't, you're right. It's like, but on a reality level, like physical level, I mean, we can't change our reality just by looking at it, right? I mean, I think people take that quantum idea and then they extrapolate it out in ways that maybe aren't appropriate.
I think you're right. And I don't want to pick on the New Age movement. Actually, I've had the opportunity in the past couple of years to meet with Deepak Chopra.
Oh, well, that's great.
And he is really, just to wax eloquent on him, he's a wonderful, warm-hearted, kindly person who genuinely wants to understand quantum physics as it is. He's got his own ideas philosophically and metaphysically that I don't subscribe to, but I don't think there's any effort by him or others to distort the theory. They're genuinely, as we all are, trying to make sense of the world that we live in and its meaning for our own lives. Now, having said that, I think that we have to be careful about extrapolations of ideas from really deep physics to our daily world. It is true that by observing things, we alter them. That's true of life, everyday life. This is true of the quantum world as well. But it's not really the same thing. It's a different principle applied in two different contexts. We're interconnected. You and I, by virtue of the adventures we've had together, have exchanged particles that we carry with us and have a bond between them. And in principle, if you could extract them and measure them, they would show a correlation. That's the quantum entanglement. But that's not really the connection between us. That's just kind of a product of our atomic composition.
Yeah.
So you can't really understand, I think, the deeper aspects of human nature through these physical terms. People often talk about fields, idea of a quantum field. Again, a technical concept that has a lot to do with the way the world was put together, but it's not something to meditate on or mention in your yoga class. It's not really relevant to that level. So
yeah,
as I am with other, I tend to think of knowledge as related, but ultimately still stratified. That we have physics, we have sociology, we've got kind of moral principles to live by, and they're of course related in a sense, but they're not the same.
Right. Yeah, there's I don't know if you're familiar. I'm kind of really going on a tangent here, but if you're familiar at all with the philosopher Ken Wilber, do you know him?
No.
He's like a New Age philosopher, but he was trying to put together all these different disciplines into one framework. And so his idea was that, on one side you have things that are this kind of interiority, which is consciousness. On the other side, you have exteriority, which is where science shines. And interiority would be where like meditation and psychology kind of live. And then the other axis was, individuals and sort of collectives. So you could kind of put these disciplines into this meta framework. I don't know how well it really holds together, but it was an interesting idea and definitely influenced the way that I think about those things, which is that they're kind of separate domains. One dealing with the interior, one dealing with the exterior. But
cool. I made a note about that. I want to look at it because part of this book project, part of what I'm thinking about a lot these days is physics has its own interior, and science in general, natural science, has its own interior versus exterior dichotomy, and it needs to be understood because there are situations that come up where we are trying to take an objective physical description and relate it to what an embedded observer would see.
Yeah.
And often that embedding is not at all obvious, and it's not even obvious that the embedded observer will see that same set of laws of physics, and you try to understand that and how to relate those two levels of description. I think that's kind of a lot of thinking in physics, foundational physics today, kind of comes back. It comes up in the multiverse, understanding what parallel universes, for example. The whole reality is countless parallel universes or parallel worlds or parallel realities, but we find ourselves in one of them. How do we relate those ideas? Which one do we find ourselves in? Can we tell?
Yeah.
How does that affect our reasoning to know that we're one of a vast kind of ensemble like that?
So one thought is that this sort of collapsing of possibilities that you see in the quantum world, maybe those other possibilities exist in another parallel universe?
Yeah, there's different ways of thinking about and phrasing it. One way is, yes, there's a bunch of universes and there's different types of, I should say, parallel universe that come up in different domains of physics, and maybe they're related, but let's focus on the quantum one for now. So that to take the simplest example, shine a photon at a beam splitter. So it's basically a mirror that's partly silvered. So sometimes the photon will go through and sometimes it'll reflect off. You can actually use that, and it is used. You can go online and look for it as a random number generator. So if you want to basically have a perfect coin toss for your soccer match or whatever, you can actually use this in principle where you shine the photon, it goes through. It reflects, it goes through, reflect, and whatever. That's going to be a completely randomized process.
Yeah.
So the question is how to interpret that. And one way to interpret it is there's a lot of universes. In some, it goes through. In some, it reflects off. It's random to us. It's completely deterministic on the larger scale, but we only see a small fraction of that larger scale. And it's random to us because we just happen to be in the universe. So the randomness is kind of on us.
Right.
We happen to be in the universe. And Sean Carroll has a very nice new book that goes into this. Of course, there's been a lot of written by me and others on this kind of mini worlds idea. And you have to be you have to start thinking about what does it actually mean, another universe?
Yeah.
So it's, in this context, it doesn't actually mean a kind of mysterious patch of planets and stars way out there. It actually means it actually just comes out of the quantum description, that within the quantum description, there are what we call branches, and each branch has the state of the photon and the state of me observing the photon. And those two are disjoint. So we're in the same world in a quantum sense, but they seem disjoint from our kind of classical perspective. So again, it kind of comes down to our limitations as observers, and probably they're inherent in what it means to be an observer, to be a conscious agent, that we are necessarily restricted in this way.
Right.
But this was really a great insight of Hugh Everett in the 1950s, that up until then people, well, there have been a range of ideas, but the majority view was that upon measurement, the wave function, this quantum description, would collapse.
Yeah.
And the act of observing that photon in this case would cause it to go through or reflect off that little prism or that little mirror I just described. And they thought this because, well, we don't see particles both going through and reflecting off. We just see one or the other.
Right.
Ergo, there must be a process to distinguish those two. But Everett's view was actually, no, they could go through and reflect off. And it's really our inability to see both. It's kind of our limitations as observers that bias us to seeing one or the other.
Yeah.
And there's lots of other explanations, by the way, that, there's 1,000, whatever, large number of explanations for what's going on here.
Yeah.
This goes back to this, what I call the number one mystery in physics right now.
Yeah.
Is kind of reconciling that.
Yeah. Well, and it seems like also, I was just thinking that, if this was true, that there were these multiple states of existence, and you think of all of the coin tosses essentially that have gone on since the beginning of the universe. I mean, if there was another universe, if there was a parallel universe, it could be so radically different than our own, because it seems like a lot of these things, again, I'm looking at this from a biologist perspective, are just sort of happy accidents that at least in biological terms, things could have gone very differently. But there's a history there of the way that things went almost randomly. I don't know if that applies also to like astrophysics and stuff, but
this randomness is pervasive. Now, the science fiction writer Ted Chiang has an amazing new book of short stories. I think it's called Exhalations, that everyone's got to read who cares anything about quantum physics, because there's two stories in there that bear on this question, kind of spin out some of the meaning of it, and it addresses the very question you brought up, where he describes how after in this case, this photon passes through, and you can kind of follow those two sets of worlds, those two worlds, they very quickly diverge. And he's got some very interesting analysis of the divergences and the human meaning that has. So there's a George and an Eric who've split off and are having their own consciousness. If this theory is true, if this interpretation is true, who are having their own independent existences that very quickly diverge. And it's like an example of the butterfly effect in meteorology, where a small change, I think, and he describes a study, fictional, but probably based on fact, where after like 6 months, the world is completely different. There's no correlation at all in certainly the weather patterns, even from a single particle. Can have a huge effect. And this is one kind of weird and interesting and puzzling aspect of this many worlds interpretation, is precisely that understanding kind of the divergences among these worlds and calculating the probabilities that then arise. Yeah,
and as you said, it's probably hard, and it gets back to that question of, if there are these little things going on amongst particles, does that then translate to the larger world, which is that fundamental question. So maybe there are little particle mini-verses, but maybe not for a separate George and a separate Eric,
Yeah. So anyway, that story is one of the most provocative things I've read on quantum mechanics in a while. So really got me thinking about what this would really mean. Yeah,
that's I'll have to check that out. So we've We've definitely, I think we've done a good job of covering just how weird quantum mechanics is and some of the implications of what it means, and maybe the limitations of our own conscious minds in understanding it. But what's interesting is that, as we mentioned at the beginning of our conversation, there was this news now that people are using this quantum weirdness to actually do stuff. And I think that's one thing that people really don't understand, is that, you know, an understanding of quantum mechanics and entanglement is allowing us to do things with that we haven't been able to do before in sort of an engineering sense. So how can we use, how did Google use this strange phenomena to create this supercomputer that can churn through tons of information and spit out something that would take an IBM computer, 10,000 years or whatever they said? I forget.
Yeah, right. So just to provide a little bit of context here, quantum mechanics, being a theory of the world, of course, is going to have technological applications to it because it's such a pervasive set of principles that are applying here, and it have indeed been used in different ways for lots of, like the laser, the transistor, solar cells. These are technologies that involve quantum principles at some level. And kind of what's really happened is we've seen other quantum effects be harnessed. So one was this quantum entanglement that I spend a lot of time in my book talking about. It's been harnessed for cryptography, one type of quantum cryptography. And essentially it provides a check. Because of the ways particles are related, you can use it as kind of a way to check if your message has been tampered with. So if you're trying to communicate and you want to know if someone's listening in, there's kind of a ironclad way using quantum entanglement to tell. So you can use Signal or one of these apps, WhatsApp or whatever that's encrypted. You could actually, in principle, use a quantum encryption and actually guarantee the NSA and the Russian hackers aren't listening in on you. And now we're seeing, and it's been developed for 20 or 30 years, since the 80s really, a whole computer based on quantum principles. And there's lots of reasons you would want such a computer. For one thing, the different aspects of quantum physics help you with that. One is that a quantum particle or a quantum system of particles is extremely information rich. So normally, if I have 3 particles, just take a simple thing.
Okay.
I put 3 bits of data on that.
Right.
So 1 bit on each particle. But in the quantum world, I can actually put 2 to the 3, 8 bits. Actually, even there's a multiplier on that. So actually even more than 8 bits, but just to take the basic scaling here, 8 bits on that. Because what's happening here is the data is basically collectively being held by those 3 particles. They're not just limited to each particle acting independently, but there's relations, these entanglement relations, in fact, among them that allow them collectively to hold more information, and it scales up exponentially. So 4 gives you 16, then 32, and every time you add a particle, you double a particle that has 2 states, as these particles usually do.
So let me pause there just for a second, because I think we talked to you threw in a couple of things that people might not understand. So one is the way that bits in computer language typically work is there's a 1 or a 0, right? So there's 2 states that each bit can be in, and that really underwrites all of our computer language. That's right. Am I saying that correctly?
Yes.
Okay. Yes. And then quantum entanglement is, and maybe you can explain it better than I can, but in fact, I know you can because you wrote a whole book on it. But is there a way to explain that in like a sentence or two so that people can understand just on a basic level what entanglement means?
Yeah, I don't think there's any need to even give a full description of entanglement because it's an interesting phenomena. I think in this case, what's important is there's a collective storage of information among these particles.
Okay.
That they're stored by virtue of their relations among them. So what you can, for instance, say, what's a good way to put this? In the case of those three particles, mm-hmm. you can imagine that the three particles are, say each particle itself can be described as 0 or 1. Each particle is a bit of data. So you might have 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. And there's 8 of those possibilities. And it turns out that all of those 8 are present to some degree, or can be present to some degree, in the system. And again, it's almost like a cat's cradle of relations among those three particles is maybe the best way to think of it. Uh-huh. That so this is separate from some of the other implications that entanglement might have. In this case, we're just looking at the relations among these particles, such that the whole is more than the sum of its parts.
Okay. Right. Okay.
So that gives you huge kind of scale up, obviously. So the Google system recently shown had, I think, 53 working bits in it.
Yeah.
And the other companies like IBM, Intel, and Rigetti and so forth have similar numbers, 50 or 20 or 30, but roughly the same number. So they have 2 to the 30, 2 to the 50, 2 to the 53 possible states or possible kind of places to put the information, because the whole is so vastly more than the sum of its parts. In fact, the parts at that point don't even really matter.
Yeah.
The whole is really taken over.
Yeah.
So you've gone 53 to 2 to the 53 is just like, it's an incredible increment. Yeah. So that's really one of the specifically quantum advantages here. So and just to riff on that a little bit, once you've got this incredibly compact way of storing information that just a handful of particles can store all the information humanity has generated in principle, you can manipulate it. So it's not just that you're storing it compactly, it's that everything you then do, every operation you perform, acts on all 2 to the 53 effective logical bits of data that are there.
Yeah.
And this comes in handy really, and this is what my Quanta article that you were referring to on machine learning really talks about for machine learning, because you can manipulate an enormous matrix of numbers, an enormous grid of numbers.
And we can link to that in the show notes, by the way, for people listening.
Right. Yeah. With a single or few operations. And basically the idea is in the future, right now all those matrix calculations in machine learning and AI are done by GPUs, by graphical processor units that were developed for gaming, really.
Yeah.
And now, I think in 10 years or X years, they'll be done by QPUs, quantum systems, because the quantum basically can also manipulate matrices, but even better than a graphical processing unit can. Quantum mechanics lives for matrices. It's matrix-based.
Yeah.
The whole algebra of it is matrix algebra. So if you can live in that realm, and there's problems to do that, I don't want to minimize. There's conceptual and technical problems. But if you could, you'd have this enormous advantage.
Yeah. So when you're talking about graphical processing units for gaming, and the way that those scale, it's not exponential. It's just you're just running more processors in parallel, correct?
I mean, I think there's some a high degree of parallelism on it. I'm not really familiar with the architecture.
Okay.
But ultimately, they're classical devices. They're limited by the classical physics. So if they want to multiply, a column of numbers and a row of numbers to give you a matrix or whatever, or to give you a single number, they're performing one by one multiplications. And maybe they've got a good way of doing that. Probably they do. They have a number of multipliers working in unison. I should know this better because actually one of my projects as a college student, I interned at Jet Propulsion Laboratory, and one of the things we did was work with parallel processors of the sort. It's distant in my past.
Yeah. It's been a few years though.
Yeah. So, but anyway, but the quantum is just a whole different degree of capacity. It naturally does it all with one go. Right? It won't have to just go multiply this all in a row. They'll just do it.
Yeah.
And it acts collectively on the whole system. And as I said, that's just what you want for a lot of machine learning applications.
The thing, and I did read your article. It just seems to me like a bunch of gobbledygook. Let me put it another way. It just seems like I don't know how you could get it like an answer out of this system. It just seems like it would just spit out a bunch of nonsense, because how do all these parts like interact together to produce a result that you want? Maybe you could give us like an example of a task that a quantum computer would be able to do better than a classical computer.
Yeah, well, there's a couple stages before I can like trot out specific examples, because there's a lot of subtleties here.
Yeah.
But basically, you put your finger on the difficulty with this system. So there's nothing mysterious going on here. It's just a natural system that happens to, in its workings, you rely on matrices. It's just like saying if I throw a baseball, I use calculus to calculate out its path and when it'll fall back on the ground. It's as though the baseball embodies calculus. So similar thing going on here. If I can encode the quantum systems run by matrices, the baseball by calculus. I mean, in a loose sense, of course.
Okay.
So if I can get my data in a form that the system embodies, it will then naturally, of its own accord, do the calculations for me, and then I have to extract it back out. So it's the problem is the encoding and the decoding, actually. A system's just doing what comes naturally to it. It's just following the laws of physics that apply to it.
Yeah.
In that case of matrix algebra, there's nothing kind of gobbledygooky about that. It's like everything in the world follows its own set of principles, and if you can somehow work in its language, then it'll just do it on its own.
Yeah.
And but that's the trick, is you need to translate your problem into something it recognizes, and then translate the answer it gives you back into something you recognize. So with ordinary computers, we're always undergoing translations. You're translating a key press into an electrical signal. That puts it in the microprocessor's language. Then does, through the transmission of electrical signals, what it is wont to do.
Yeah.
Then you need to, at the other end, put it back into a pattern of light on your screen, let's say.
Right.
Nothing bizarre. And all that's changing with the quantum is now there's a different set of principles at work.
I see. Okay.
That makes sense.
Yeah, I think that helps.
Now, the challenge of these systems is the translation part, and the challenge is heightened for these quantum systems because of the vast amounts of data that are required. So somehow you can take a vast amount of data and compress it down, get it into the quantum system, then unpack it on the other end. And that's really where the challenge lies.
Yeah.
Now, there's ways, and this is kind of getting into some of the applications that you wanted me to get at.
Yeah.
For the system to help you with the unpacking process. So if you have 2 to the 53 bits you put in, and then you get 2 to 53 bits out, I mean, you might be waiting forever for that, right? It's going to take a long time to dribble that data back out through ordinary wire.
Yeah.
But if you have the computer itself manipulate the data, so only you need like 4 bits to come out, like it packs all the essential information into just a few of those channels, then you're golden.
Right.
And the way it can do that is through a second basic feature of quantum physics called interference.
Okay.
So what you do is you have the different data within the system, maybe all the way up to 2 to the 53, are interacting with one another. Sometimes they cancel out, sometimes they reinforce. And if you do that cleverly, and that's the trick, of course, you can get out an answer very, very compactly.
Okay.
Otherwise, in fact, you really are going to get a gobbledygook. You're going to get you have a wire. It's going to take one of those 253 and randomly choose one for you, in essence, and give you one out the wire. I'm kind of brushing a lot under the rug.
yeah, no, I get it.
So, and here's the thing. Physicists only know of a few examples where that kind of compact description will occur. So one is search. So basically search a database. There's a way to arrange this interference such that you can very efficiently search a large database. So if you were to take those 2 to 53 bits and actually encode the corpus of Facebook images, you could somehow on the other end search those images and come out with a puppy or whatever.
Yeah. So that's one. And the other just want to get out is factoring. So there's ways of factoring numbers into their prime factors very efficiently using this. And that's really what people are when they talk about the application of quantum computer, that's the one they mean. Yeah.
Because factoring does all sorts of other things as well.
So is Google's primary interest in this as a search tool for finding images or finding the thing that you want?
Yeah, I mean, I think Google has a lot of interest in it. They're obviously mega company.
Yeah.
They do everything nowadays.
Yeah.
Probably they want to do some of these machine learning applications early on. I'm guessing.
Yeah.
You'll test them. It's a little bit far to really know, but that's an early application because it doesn't require the machine to work as accurately as other like the factoring would.
Yeah.
Or the search would. But ultimately, I'm sure they want to do search and factoring, and there's a few other algorithms as well that can harness this quantum interference effect to great things. Now, what's happened with the Google Supremacy, so-called quantum supremacy experiment, is really akin to the Wright brothers flight. It's just a proof of principle. Mm-hmm. And I don't think I've heard anyone else put it this way, so I'm going to give you kind of the way I think of it. Uh-huh. So up until now, if you want to understand a quantum computer, you're better off simulating it on a classical computer. So IBM actually has a quantum computer online. You can register, you can go on, you can actually run a simple app on their online cloud-based quantum computer.
Interesting.
And they have a button there called simulator, and you're actually faster running it on the simulator. So simulator is just a regular computer, applies the laws of quantum physics, and tells you what the quantum computer would say. So a quantum computer is faster run as a simulation or emulation than as it native.
Interesting.
What's changed with Supremacy is just flipped the other way. The quantum computer now is faster than its simulator. Uh-huh. So it isn't so much that it would take 10,000 years or 3 days or whatever to run that calculation on a supercomputer. All that matters is it flipped. It's faster to run it on the quantum computer. It's faster to do it on the actual thing than it is on a simulation. And now that's going to be true for the rest of eternity. So now we're entering this kind of new realm where quantum computers are natively faster, and it's going to be a matter of finding the right algorithm for them to run.
Yeah. So when you're talking about the difference between a classical computer and a quantum computer, what does that mean physically? Like, what are they made of that's different?
Yeah, I mean, we're still in an experimental realm, so the final form these quantum computers take, who knows? They'll probably be something you can plug in on your USB port or whatever in the future. But for now, they're pretty, massive pieces of apparatus. Fill up the lab.
Yeah.
Typically, it depends on the technology, but typically they have to be super cooled. So there's a cryogenic system that brings them down to very low temperature that reduces the error and the kind of the noise in the system. And then, again, depending on the technology, you might use lasers or a microwave pulse. So in the microwaves you have antennas around the system that beam microwaves or receive them out of the system to kind of do their input and output. Some of the systems use magnetic interactions, electrical. So there's a wide variety. In fact, that's what's so fun about this is there's really a thousand flowers blooming on this. There's a lot of different technologies. The Google group uses superconducting qubits, but others use ions. And one kind of technologist, there's a group in Netherlands working on it, uses just ordinary silicon. And this is maybe the most conservative technology, and maybe the one that will ultimately succeed, because it's actually just using ordinary lithography on a silicon wafer, storing the qubits, storing the quantum information just by electrons, ordinary particles like we have now in these computers.
Yeah. So I guess there's a lot of different ways to get that quantum entanglement state, different particles. I just wanted to mention the videos that we made on that. If people want to know more about quantum entanglement, we have one video that this is when we worked at Scientific American. We did a video about the principle of quantum entanglement using a kind of ridiculous experiment with people, and then we actually went to a lab where somebody had set up a table with lasers and crystals that can achieve that as well. So I just wanted to plug that because we put our heart and souls into those videos, and glad that people are watching them. But and
there we focus on kind of the mysterious qualities of entanglement that, in particular, it doesn't seem explicable by mechanistic physics. So in physics, we always want to explain things. We want to say, well, we're going to break it down. And the clock works because the gear turns and the pendulum and whatever. And that's something we can't seem to have an equivalent description for with entanglement.
Right.
It's part of the mystery of it. Now, given entanglement, if you don't want to explain it, if you just want to use it, then you're in the realm of quantum computers, and there's no problem there. You just use it. It's only when you want to get at it at a deep level. And I think quantum computers may help ultimately with that, because we're just better do stuff with entanglement, and often we just learn by doing. By doing a lot with it, we're going to go, I'm getting to get it now. I kind of get why it does, why, and we may understand it, or we may see its limits. Some people, it's a minority view, but some people think we're going to hit a brick wall. That there's going to come a point where the quantum computers won't work.
Yeah.
I don't think that. I think quantum physics is here to stay, but there may come a point where it doesn't work, and then that's a Nobel Prize right there.
Yeah.
And as you just get on the plane already to Stockholm, because that's going to be telling us the limits of quantum physics.
Right. Interesting. So the application will tell us more about the principles themselves. I think so. That's so interesting. Well, we're at about an hour. I think we could probably talk for like 8 hours on this, but for the sake of the podcast, or more. I think for the sake of the podcast, we should probably wrap it up. I did want to ask you one thing, because you mentioned you're looking at quantum computing and AI and machine learning. With this incredible computing capacity, do we need to be worried that these machines are going to replace us? I mean, are they like better? Are they going to work better than the human brain can, or does the human brain sort of already use some of this phenomena in the way that it functions? I know that a couple of episodes back, speaking to a neuroscientist about how the brain works, he said that's the fundamental question in neuroscience, is like they don't really understand how it all sort of works together. So maybe there is some quantum principles underlying how our actual brain works. What do you think? So
there's really two questions there.
Yeah.
One, does this heighten our worries about AI? And second, does it mean that there's quantum effects in the brain?
Yeah.
I think if you're worried about AI or not worried about AI, the quantum aspect's not going to really change things. It's going to be a long, long time before these quantum computers can outpower the Google and Amazon, data centers, which are massive. So right now it's really more of a niche technology. And this whole question of whether we humans are existentially doomed will be resolved one way or the other by the time these quantum computers scale up. So if you're worried, you're still worried. If you're not worried, no reason to start worrying.
Right.
That's a separate debate.
Yeah.
And I go back and forth on it. Right now, I tend to be optimistic. Actually, I don't think we're going to be replaced, because I think humans are basically going to enter that new era as a highly general type of cognitive machine and robot. We won't be better at any one thing. We'll be worse at driving, worse at chess, worse at Go, but we'll be the only thing on the planet that can do them all. And there'll be some benefit to that. But that's a separate set of questions we can come back to.
Yeah.
So there's been a lot of discussion about quantum effects in the brain, and I do think, and there's a lot of controversy, but I do think that the success of quantum computers gives you pause, because if the quantum computers are so useful, why hasn't nature,
Yeah.
after billions of years of evolution, basically stumbled on those principles? It may well have. Now, I think if it has, it won't be a general explanation for consciousness, as Roger Penrose or Stu Hameroff would say. That's just my opinion.
Yeah.
I don't think it's a general. I think it might have a specialized application. If it has an application, it will be specialized, much as quantum computers will be in our technological world. So there may be some aspects of perception and cognition that quantum helps with. And the examples that have come out so far in biology, so you know more about this probably than I do, is photosynthesis. There's thought to be a role for quantum coherence in making it more efficient. It's kind of a more efficient process than it should be, and maybe quantum physics helps. So that's a specialized, useful, God knows, but very specialized application. The ability of birds to perceive magnetic fields might be that there are electrons in the retinas of the birds that are being subtly affected by the magnetic field, changing their quantum superposition, and they scale that change up. It's not entirely established in these cases. There's been several books on what's called quantum biology, so you can Google that or put it in Amazon. I've actually got one on my desk here by Paul Davies, recently came out. But there's quite plausible there's somewhere in our body that uses, in an essential way, these quantum principles. I don't think it's general. I think our brains do just fine without quantum principles overall. We don't need this massive scale of data that it provides.
Right.
We don't need the extra connectivity. Our brains are highly connected classically, but there may be something in there that it does help. Right.
So it might be a specific function rather than kind of the thing that holds our consciousness together, as you said. It's not fundamental.
Right. And one reason I think that is our brains already are highly capable, even without that. So it would just be overkill.
Yeah.
But also, I don't see how quantum physics could help with the hard problem of consciousness. So the hard problem is that our objective physics doesn't seem to just explain our subjective experience. But the objective physics can be Newtonian or quantum. It's still going to have a problem for our objective experience. So quantum doesn't help you with that.
Right.
That's just my take. I mean, others disagree.
Yeah, that makes sense. Yeah, it's still an objective viewpoint, which actually perfectly brings us back to what we were initially talking, sort of the New Age, about the New Age stuff and interiority and exteriority. So I think we'll just have to leave it there. But George, it's so awesome to talk to you. Seriously, it's always so interesting. I'm really curious to see where this all goes. Hopefully we'll be around to see it. And my hope personally is that all these advances in technology are also going to have applications in medicine and advance us, with disease and genetics and all of that stuff. And we can put some of these machines to work on those thorny problems that we'd rather not, have people sitting in labs pipetting things, and we can put the machines on it, so to speak. So where can people find you? Where can they get your work? Where can they get hands on your books that you've written?
Well, the bookstores all have it, of course, but georgemusser.com is my main website. Spookyactionbook.com.
Okay.
Which just goes to georgemusser.com, so those are really identified. Would be to start, or just Google my name.
Okay, cool. And you write for, you're still an editor for Scientific American, contributing.
So I'm what's called a contributing editor.
Uh-huh.
So I do a lot of work for them still, although I'm not on the full-time staff anymore.
Yeah.
And I also write for, as you say, Quanta.
Uh-huh.
I've written for them. I'll hopefully write for them again, and other publications as well.
Cool. All right. Thanks a lot, George. It's been awesome.
Thanks. Take care.
Well, that's it for this show. If you learned something new, be sure to smash the like and subscribe buttons. Also, click that little bell icon to get notifications when new episodes go live. Finally, I'd love to hear your thoughts on this episode, so please leave a comment or question below. Thanks for watching, and I'll see you next time.